All right, welcome back to CS50. This is the end of week 7. So there's one handout today, and it might feel a little early, though granted the calendar has changed, so it's going to be a little earlier. But I wanted to draw your attention to one of the URLs that's listed on this handout. So CS50's final project is, as we say in the syllabus, the climax of this course. It's going to be the time where you guys get to choose what you do, how you do it, and what you ultimately make of the course. And these photos that we've been showing are this thing called the CS50 Fair, which we actually started for the very first time last year. And it was actually, for us, a whole lot of fun. We had, again, all 300+ students last year. We had 600+ of their friends and family and random folks on campus join us in one of the science buildings down the road. And it was just an exhibition and an opportunity to hang out, to chat, and to see on each other's laptops exactly what you pulled off this semester. Now, you might be feeling that thus far we've been handing you most of what you're capable of. So we gave you a framework for PSET 3 and for PSET 4 and a little bit for PSET 5. So we're going to have to come full circle and take those training wheels back off by the end of the semester, and you will be able to do that because in the last 2 PSETs of the course, 7 and 8, these will be web-focused, which caters in part to the interest among students in recent years to do web-based projects. But odds are you guys are going to want to go off on your own quite possibly and do even more than the course itself officially covers. And so the teaching fellows, CAs, and some alumni and graduate students have kindly offered to put together this suite of seminars. So these seminars are optional. They will be scheduled in early November based on level of interest and on your actual schedule, so more on that to come. But we ask right now that you RSVP for any of these things of interest. There's 11 on the board. Just to skim a couple, iPhone development has already proved popular. Though you probably won't make in just a couple of weeks the most amazing iPhone application, you can absolutely do something that excites you. And you can certainly build on it if you choose in, say, spring term. And a seminar like this will help get you started. Those of you interested in making Facebook apps that your friends might actually use, we'll do a seminar on that as well. And then a whole bunch of other topics. Another is this Android cell phone platform. And let me make explicit mention on this, which we did on Monday already. Google very kindly donated some cell phones to the course. We are happy to give these to those students who would be interested in tackling Android projects, but do go to the appropriate link here and find out who to contact, namely me and one of the CAs, if you would like to tackle an Android-specific project. And we will attach a couple of conditions, like you really should have T-Mobile already or AT&T, because again, these are GSM phones. But if you're interested, express an interest now per those directions, and we'll get you started. But there's a whole diversity of projects students did last year. And if you get a chance at some point, go to the fairs page where we have a bunch of videos. And I see some of the TFs have started enhancing their privacy settings. So some of these videos are no longer accessible. So we'll fix that. We have archives. But you'll also see at the top of this page a link to last year's program. So it's rather inspiring, if not maybe admittedly a little intimidating at this point in the course. That's the wrong link. This program here. This is the official program that we handed out to attendees last year. And some of the specifics now you shouldn't care about. But if you skim this, for instance, these charts, you'll see what kinds of languages students last year actually used. So yeah, the course teaches C. The course teaches a bit of PHP and JavaScript. But your predecessors bit off a whole bunch of other stuff, some of which they came into the course with, some of which they absolutely did not. And you can actually see titles and descriptions for all of last year's projects here. And you probably will see some familiar friends' names. So do check that out. It's on the fair page. And do RSVP per the directions on the seminars page as soon as you get a chance. Let's see. Any questions about that? OK, so even though PSET 5 isn't yet due, it's been striking how many surveys have already been submitted for problem set 5. I dare say it's a lot more fun and procrastination-worthy to click little bubbles and fill out circles and stuff online than to actually do the PSET. So we've got over like 200+ surveys that have already been submitted, and like 5 problem sets that actually came in already. But that's OK. But it meant I was able to start reading through these things. Because all the better, I think, for me, if we start absorbing some of your feedback, good and bad, and see if we can't make the best of the remaining weeks in the course. I will personally make sure to read all of these surveys that still come in. So don't think that those gates, that ship has sailed. But I thought I would excerpt some of the more serious comments that were posted, and then also some of the more memorable ones. One student, one classmate, noted in answer to the question, what have you learned in the class? Well, we always enjoy things like this. So that's good. But this one was clever, because we know the course is challenging, especially for a non-trivial percentage of the class who's not programmed before. This was just cute, I thought. But what's sad is that you understand this kind of humor now, so I'm not sure that's such a good thing. But let me address a couple of things in series, and these are recurring themes. So I was actually thinking, unrelated to the surveys on Monday, that it's actually pretty hard teaching in this space because it's very cavernous. Even I can hear my voice echoing in this room. And it's hard, I think, as a teacher to actually reach out to you guys. And I can kind of sim the audience and make you guys feel as best I can like you are in CS50 and this is just an awkward one-on-one conversation right now that you'll always remember now. But it's hard, in this room especially. And some classes for years that have been in here resort to this Oprah Winfrey style approach of having mics in the audience so you guys can stand up and ask your questions. And I can't imagine anything more awkward. And frankly, we'd get all of the Gov majors in the room, perhaps asking questions instead. And I remember I was one of them at one point. So realize that I've actually been feeling this frustration myself where it's hard to kind of connect in this room. And I very often feel like those Simpsons moments where Skinner is standing up on stage, he says something stupid, and the whole middle school is silent, except for that awkward in the background that makes you realize just how awkward it is. So I hope you guys will raise your hands more often, or, and I'll address this with some specific comments, like raise your hands not when you have answers, but when you have questions. And I'll admit, it's hard for me to hear things up here. And I realize it's a little awkward to say, I don't understand something, because you literally have to speak loudly so I hear it. But I'm hoping we can address some of these comments by just making this even more interactive, and so that you don't feel like you're exiting lecture having completely missed something, because there's no point in my plowing ahead and teaching something that I think I'm teaching well when clearly I'm not. So please help me fix that by raising hands as often as you are inclined. And if your hand is one of those going up too often, don't worry. I'll start to focus more on these students than, say, those or something like that. But the workload in the course. So one of 4 themes that has already come up in the surveys, and I'm sure will come up in the remaining couple of days. So this course is a lot of work. With that said, this is all relative, because we often hear this from, frankly, freshmen and sophomores whom are, this is a lot of work. And I think perspectives do change over the course of time, so keep that in mind. But this is very much intentional. And as I said in the first week of the course, I mean, this really is kind of one of those courses, one of those fields where you really only learn by doing. And if we were handing you problem sets that were half as long or quarter as long, I mean, I dare say you would get half as much out of the course's experience, or a quarter as much. And we like to think that this course, by contrast, is, yes, one that absolutely expects a lot of you during the course of the semester. And for some, really squeezes your brain. But whether it's going to be in January of 2010 that you look back and feel, damn, that was for the best, or even several years from now when you look back on this course and maybe others that are kind of kicking your ass, so you may feel right now, I think that's, frankly, why you are all kind of here. And I know I don't want to sound all too lofty, and I realize all of us have way too much going on, right? To a fault, Harvard students, myself included, probably bite off way too many extracurriculars. Yes, you have 3 other classes. So realize, if nothing else, we appreciate where you're coming from. But this is why there's 60 staff members for the course, and why there's a bulletin board and office hours and all of this other stuff, because we are certainly going to get you through the experience. So realize we hear you, but please do at least meet us halfway with those resources. OK, grades, too. Quick on this. So being Harvard students, too, grades are of predominant interest in many courses. It took me years until graduate school to kind of calm down. And I was absolutely one of those kids in high school and even through college that, like, work came first. And frankly, I didn't even like school all that much. I just was kind of conditioned as a kid to work hard, do my work, get my A's. And, ironically, it probably helped me get into grad school and get me where I am today. But it wasn't until grad school, having worked for 3 years after college, that I realized, there's kind of more important things than worrying about grades. So not doing well, but worrying about grades. And I say this because this course does take a somewhat different approach from a lot of the sciences courses, math courses, where it pretty much is right or wrong, check or uncheck, plus or minus, where you can get a very qualitative response. And I know some of you, per your own feedback, have been feeling frustrations. And this happens every semester, certainly that I've been teaching the course, where you feel, hey, I have undergrads being my teaching fellows. I'm getting very subjective. I'm getting very disparate feedback from all of them. And I know I've said many times that we will take all of this into account. And you can talk to past students about just how many of them were disappointed or not with their actual grades for some data points. But realize we view the course much more like, so far as grading goes, a humanities course, where if you're trying to write an essay, it's really hard to say this is 95% or 75%. And we could do this with problem sets, like check or plus or minus, you got this correctness metric right. But you'll hopefully realize now, if not eventually, that programming and solving problems is not just about yes or no, it's right. It's about how good it is, how fast your code is, how intelligent your code is. And honestly, these are only things that can be evaluated subjectively and qualitatively with handwritten or typed feedback and less with numbers. So realize that's very much a design decision. I am quite certain that we will never convince some of you in the course of just this ideology when it comes to grading. But do realize, and perhaps consult past students, that it does tend, I think, to work out for the best. And please speak with me personally if you are concerned about any specific specific scores. So with that said, my availability. No one ever comes. So this is linked on our course's homepage, my own URL. So these are, OK, that's maybe why no one comes. All right, so these are my office hours. So please come if you feel that I'm a little too aloof or just this big voice on stage or, God forbid, like worse, scary or intimidating. Just please drop by. Drop me a note, because frankly, I tend not to be there. But I will be there if you want to be there. And I essentially block off these and other times to sit down and chat. So reach out. There's no reason I should not be accessible. A little interesting. All right, and finally, so now I'll go back to a couple of actual comments. I'm not the only one hearing that, right? Interesting. All right. Maybe it's this live wire. The iPhone has fixed it. All right. So these were some comments that were directed about lectures and content, because one theme that's very common in this course, and frankly in all the courses I've taught for 10 years, is the rapidity of my voice or the speed of class. And I don't necessarily think that moving fast or relatively fast is a bad thing, because the flip side, of course, is that the course can risk going too slowly. And this, too, is one of those things where there is no chance that we're going to please everyone in this course. Much like it will be very difficult to ever get 100% consensus that, yeah, course is going perfectly. So we do our best, frankly, to displease this half of the class and displease this half of the class. And so everything kind of averages out. I mean, that's kind of the way of these things. So we try to walk this fine line between going too fast and going too slow. Because the downside, of course, is if we devolve into something too slow, then there's other people who don't want to be here. But this is the bigger question in my mind. So we now compete, or people like me compete, with videotapes, like of ourselves. And I've thought many times over the past few years, like, what really is the point of lectures? Because I would dare say that some of you, many of you, are here just because this is what you do in school. You go to class, whether or not you feel you're getting something out of lecture. And those of you who are watching this at home on video, you've made a conscious choice that this is maybe not a good time of day to be awake, or a good experience. And so it's a hard question, right? Because what is the point of lecture if you can watch this thing on video, if we have scribe notes detailing what happened, if we have slides that predict what would happen, if we have code of everything, right? Even I ask myself this: what is the point of all of us being here in this room? And so the answers I've come up with over time are, one, it's got to be engaging, ideally, right? Otherwise, who cares? Why come? Even I walk out of lectures all the time if it doesn't maintain my interest level these days, because I have many other things more interesting or more challenging, stimulating, that I would like to do. So on the one hand, my goal, whether it's with silly things like candy or with fun demonstrations with humans on stage, is to actually make this an experience. And hopefully that's not something that you get solely by watching things on camera. But two, the goal pedagogically is to set a framework, a mental model each week, so that when you do go into sections and you have those aha moments with your TFs, oh, that's how you implement this, or that's how it works, that at least you've been prepped with sort of a big picture understanding of what is a data structure, or what are linked lists, in general, what problems do they solve. And then it's when you actually get into these more intimate environments with your peers that you can really, sink your teeth into something more concrete. So there's a line, too, that I try to walk carefully between dwelling too much on code and syntax, which I know can get boring quickly, versus not doing enough of that, so that you walk out of here thinking, what the heck just went on? And so these are the kinds of comments that give me pause and definitely make me worry. And granted, there's other comments. There's good comments that balance these things out, hopefully, in the whole. But so one, thank you that I'm nice. But two, so something like this, we can address, right? Because hands can go up, and I can pause more frequently. So realize that I'm happy to try to address these kinds of comments. This, too, is worrisome, because this, too, we should fix. Because if you're not getting it, like, what the hell is the point of even being here, honestly? I don't want to be here if you're getting nothing out of this. We don't take attendance. We don't care if you're here. We want you to be here. And this, I mean, frankly, that maybe this person was more spokesperson for others. I mean, these are the 3 comments particularly that I'd like to address starting now as best we can. So whether the lectures have been good or sucked, I'd like them to be better moving forward. So please at least help meet me by trying to raise hands, engage, stop me if I'm ever doing something stupid like big white screen, certainly, but also if it's just something that's gone over your head. Now let me counterbalance the serious tone with this. So I'll offer this with no comment. So you're welcome, whoever that was. Happy birthday. And this, I know, my God, it was like a 6-page or so survey. This one was just a cute note to end on. So I'll end our discussion of that here. So let me turn our attention to where we left off in terms of content and try to do this. Try to give you a sense of, why are we here? Where have we been? Where have we been going? So in my mind in the course, and I worry that sometimes the syllabus doesn't make this quite clear, is we started the course with just setting some basic mental fundamentals, like what's a loop, what's a condition. And some of you knew that. But we had to do it because there's a lot of students in the class that didn't have that. And that's why we use something like Scratch. And then weeks 1 and 2 are kind of syntax oriented. What's a for loop in C? What's a while loop? How do you compile? How do you debug? Stuff that, again, is kind of interesting. It's kind of geeky. But 2, we have to get that out of the way. And hopefully we wrapped that kind of material in some domain-specific packaging, like the crypto, which frankly makes for loops just a lot more interesting or a lot more compelling than would a problem set that says implement a for loop that prints 1 through 100, which kind of gets to the same core material, but certainly not interesting. Then in week 4 and beyond, we started talking more about arrays and memory management. So now things are getting at least technically more interesting and certainly more difficult. And we started talking about data structures, very minimalist data structures. We had arrays. We had this C notion of a struct, where you can put multiple variables inside of some new data type. So we had the basics of data structures. And then in week 5 and now in week 7, do we take things up a notch further and talk about more sophisticated data structures? Because you can't really get through life. You can't really get through problem solving in CS or in the sciences or in any realm of life where coding is useful without having more sophisticated tools in your toolkit. So we introduced a couple weeks ago linked lists, which allow you to have data structures and storage, but that grows dynamically. But we had this linearity problem. It's still pretty slow to search something that just has arrow after arrow after arrow, because you can only go from left to right, or maybe right to left if it's doubly linked. But you had this linear problem. So this week, on Monday and today, the goal is to introduce some more clever solutions to the problem of storing data and getting at it quickly. And the ideal, the holy grail of data structures is one that grows infinitely, I would say. Right? There's no fixed arbitrary upper bound like you have with arrays, but one where your search time, your insertion time, deletion, all of those basic operations are blindingly fast, constant time even. And so that's when we introduced this idea of a hash table. So a hash table is kind of the Swiss Army knives of data structures, because it's supposed to address, ideally, precisely that problem. And we're going to see hash tables, this topic today, again in the weeks to come when we look at web programming. The goal of the end of the course is to, 1, make you realize we did not learn just C. We learned ideas that transcend this particular language, and we'll look at PHP and JavaScript, both of which use hash tables. They call them something different, but they have them. And in the remaining weeks of the course, will we really focus on real-world problems, frankly, that you might be very inclined to encounter in your own lives, whether it's for personal fun or startups or for data sets in other classes that you need to process, or just stupid stuff, like you run a student group and you get a really long list of people who've registered, and you really don't want to manually email 100 people or manually aggregate this data into some other format. You can write a script to do that. So we're going to try to use these basic ideas from weeks 1 through 8 and build and conclude the course with a look at these things that are more real world. And the final project is meant to embrace that finale of real world applications. So hash tables. So what is the point here? So it would be really nice if we had a data structure that didn't have problems like arrays, which are of fixed length. Right? That kind of sucked, because it meant if we ever ran out of space, what did we have to do? So we had to reallocate. And reallocation, even though you haven't really felt it given the size of the programs we've been writing, is kind of slow. Anytime you have to interact with the computer itself or the operating system and say, give me more memory, relative to other things, that's slow. So it's ideal in principle to avoid having to allocate memory and deallocate memory because you're just wasting time by not having had sufficient foresight. But of course, the flip side is you can say to the OS, well, give me an array that's 2 gigabytes large. I'm never going to need more than that. But the downside there is you can only run like one program at a time. So again, the theme in computer science or in programming specifically is these trade-offs. Nothing comes for free. You pay for something with time or with space or your own time, the developer's time, or just with your own mental anguish. There are things that are harder to implement, but my God, when they work, e.g. Google, they work really well. And that's not something they implemented on a Thursday night. So again, it's all trade-offs, whether it's machine-related or human-related. So a hash table is meant to address that problem of arrays. They're fixed length. It's expensive to reallocate and deallocate them. It's just stupid to have to copy your data around just to grow the space. But that's why we introduced linked lists. Right? Linked lists are these dynamic structures. So even though I kind of answered my own question a bit ago, what's a problem with linked lists? With every solution, we introduce a new problem, it seems. What's a downside of a linked list? So it takes a long time to search it. If I want to search for something, well, let's contextualize this. What might I put in a linked list? Anything. We put numbers because that's simple, but you can imagine implementing a database of students for the registrar. Well, each of those linked list nodes contains a student. What's a student? ID number, phone number, grades, I mean, all of this kind of stuff. So there are these objects in memory, but searching them requires how much time to find Joe Smith in a linked list of 6,500 Harvard undergraduates? What's the running time of search on a linked list? So big O of n, right? Because in the worst case, Smith is going to be the end of the list. Or even if they're alphabetized, he's certainly not going to be right at the middle. So worst case, an arbitrary student is going to require big O of n steps. Well, wait a minute. We solved this in like week 2. Why don't we just use binary search on linked lists? If they're sorted. Go ahead.
No, they are sorted. So they weren't.
OK, so they are sorted, but there is another problem. Yeah. Yeah, you can't access the middle of it. With an array, it was very easy. Know the end, which is bracket 0. Know this end, which is bracket 0. This end, which is n minus 1. You can figure out the middle by doing n divided by 2, and bam, you can go right there. So arrays are random access. What happens if you take the address of this node in a linked list and subtract the address of this node in a linked list and then divide by 2? Where do you end up? So numerically here, right, in the middle conceptually, but you have no idea where any of those linked list nodes might be, because the whole point of allocating them with malloc is that you're just handed a chunk of memory. But it can come from anywhere in the computer's RAM. It's not necessarily going to be contiguous. So again, we get this upside of dynamism. Now we don't have to worry about painting ourselves into a corner in terms of space, but we now have this problem that we really hurt our search time. And linear search kind of sucks, especially when your data sets starts to get larger and larger. But my God, if there's this data structure that's been promised that gives us constant time, whereby if I have a new student to insert, and let's see, I'm going to need, I won't use students here. We'll use lollipop flavors to represent distinct elements. So what I really want is a data structure where if some new student matriculates, this is not going to work very well. I really wanted a data structure where the lollipops would sit in the top, but it didn't work out. But we want essentially a black box. And this is a common theme in computer science, if you've not heard the term before. Something that does something, takes input, produces output. You don't really care how it works. You just care how well it works or how quickly it works. So my goal is to insert Joe Smith into this black box, because later I want to be able to ask a question of the form, is Joe Smith registered at Harvard? Or more specifically, give me Joe Smith's student record so I can look up his phone number or his email address. So you want to be able to insert things into the data structure, ideally in constant time, get in and get out. And then if you want that same element back, you want to be able to ask that question just as quickly. Is Joe Smith in here? If so, give him back to me. So this constant time is kind of, again, the holy grail. But how do you even begin to implement something like that? Well, we already teased you with an answer to this question on Monday, right? We used an array. We used a little picture that looked like this. Ideally, what's the ideal? So suppose we have this data structure. Let's use an array, because that's so simple. I know how to declare it. There's no fanciness. We did this weeks ago. but I decide there's only going to be 26 students. Well, the ideal student body would be that Harvard admits each year only one person with a last name that starts with A, and one student whose name starts with B and C, because then we can contrive what's known as the ideal hash function. We can implement a function, literally in code, that takes as input the name of the student and then returns as output a number, which is what bucket that student should go in. Now, what do we mean by this? Well, we can actually whip something like this up. So I'm just going to open a terminal window here. Let me increase my font size. I'm going to call this hash.c. And I just need to write a quick and dirty function here that's going to, let's see, return an int. I'm going to call it hash or h or whatever you want to call it. It's going to take as input a student, or really just their name. So I'll do a char star s to represent a string there. And the goal of this hash function is just to answer a question that the black box can use. So the black box is a piece of storage, but with it also is a hash function that tells it where to put its input, what location to put its input. So how do we decide this? Well, first, let's do a little sanity check just to practice what we've been preaching. If s equals null, what should I probably return? So I could return 1. Why do you say 1? So that it will, keep running? OK, so I do want to return something so that the function won't keep executing. Let me push back now, though, and say if we return 1, we're probably going to run into problems. Can you anticipate what the problem is going to be if the error code we're returning is itself 1? Yeah. It's supposed to return an int anyway, which means I might have just been handed null. So my answer is, oh, put Mr. Null in bucket number 1. But that's the wrong answer. We probably want to return a so-called sentinel value that indicates to the caller, maybe it's main or whoever's using this hash function, that problem happened. So what should I maybe instead return? So -1, right? A very common answer, honestly, is anything other than the range of numbers you care about. So let's return -1 and just expect that the caller is smart enough to know he should check for -1 before trusting the return value of this function. And actually, if we want to be really sophisticated here, we can do what's very common too. You know what? Let's define a constant called error and just define it to be the number -1. So now we can kind of abstract away and say return the error code called error. And now the caller can just check if what was returned is error, not -1. So there's conventions like this where we can clean up what's otherwise a very arbitrary choice like -1. OK, so at this point, I now need to figure out what actual number to return. So I've been handed a string. Let's assume for simplicity today that it's an actual student's name and that we don't have any crazy hyphenated names or apostrophes or anything like that. It's just ASCII alphabetical characters. So I want to decide what bucket to put this input in. So I just need to return a number. So maybe I can do something like, let's see, int n get, and then what do I want to do? Well, I could do cast to an int, what, s bracket 0? That will return a number, right? And then I can do return n. This will return the numeric value of the person's first letter in their name. But what's the problem here? So it's the numeric ASCII value, which means I might get back 65 or 66, probably some number that's much bigger than 0 through 26. So what's the easy fix here? Yeah, subtract capital A. That's what we've done in the past. If you want to be really anal, you can explicitly say int. But again, GCC is smart enough to realize, oh, if you're subtracting it, just give me back the numeric value. So this would work. But another approach, too, might be this. Let's see. Instead of subtracting this off, what if I do something like mod 26? Would this return to me a number between 0 and 25 inclusive? OK, so this would work here, too. And it would actually work just as well, right? Even though it would not put the letter A in location 0, it would essentially rotate the positions where things are. Would it put two people with different last names in the same bucket? Yes? OK, how? OK, so let's assume simplicity here. Capital letters, just alphabetical then. But otherwise, yes, that would be a corner case. Yeah, so no, it should work. Because our hash function is so simple and we're just looking at one letter, I'm going to even keep the hash function simple just to be ever so clear. This will return a number between 0 and 25. So now the black box that's using this hash table, this hash function realizes, oh, this is Joe Smith. This returned to me, or this is Adam Aardvark. This returns to me the number 0. So I'm going to put Adam in this location here, because aardvark, stupid name, I know, couldn't think on the fly, starts with the letter A, and that maps to 0. So we put it there. So then the question is, now we have all these students, 26 students in this black box. How do we answer questions of the form, is Adam enrolled at Harvard? Well, the black box has to use the same hash function. So now you use the same exact function given the input and see, OK, here's Adam Aardvark. What is the name? What is the location of Adam in my black box? 0. Let me now check. And if there's actually something there, the string representing the name, the struct representing the student, then I know, aha, that must be Adam. Unless our assumptions are no good. If we actually have more than 26 students, what's going to happen when we insert the 27th student and the 28th? Just intuitively. What's going to happen when we insert another person with the last name that starts with A? OK, so we can just expel Adam, right, and put this 27th person in instead. But otherwise, more generally, we get a collision. And that was the point of introducing this then depiction of a possible solution. So if we paint ourselves into a corner with an array, which even though it does lend itself to constant time insertion, notice the code. What is the running time of this code? It is constant because it takes one step to check for null, another step to check what the integral value n is, and then, OK, a third step to return that actual number. 3 steps, but that's big O of 1 time. That's constant time because it always takes 3 steps. And that's so much better than log n squared, n itself. I mean, that is very fast, and that is the ideal. But we risk this collision. So there's the trade-off. You get amazing speed, but you can only have 26 students. So again, this theme is recurring, but the theme is the result of this lack of foresight. We have painted ourselves into a corner by only having a bucket that's that large. Well, the point of this teaser at the end of Monday was to ask the question, well, maybe this isn't such a big deal. Right? Obviously, one solution to this is let's make our bucket bigger. Let's not have 26 spots. Let's have 52 spots. Right? Because then if we have more students, we have more room for them. Right? And we can find more room from them. Or you know what? 26, let's really minimize the probability of something ever going wrong. Even though we're a relatively small university, let's allocate an array for 1 million students. Because just probabilistically, the idea that we'd actually run into collisions using some kind of algorithm, it's much, much lower by nature of how much free space we have. But a downside of overcompensating is what, obviously? You're just wasting memory, right? And it takes longer to search that memory. And even though we won't dwell on this in this course, the more memory you're using, the less effective things called cache are. So as an aside, if you're the type in the class that likes hardware, you might know of concepts in your own personal computers called L1 cache, L2 cache, level 1 and level 2. All of that relates to optimizing lookups in memory. Well, just the more data you have in memory, the less likely it is that cache is going to benefit you. So more on that in a future course if you're interested. So here's a question then. Suppose we have a room full of n CS50 students. What's the probability of a collision of just birthdays? Let's make this more real, not do first names, and let's assume a uniform distribution of birthdays, which itself I think statistically is not accurate. If you read like the literature around like special events in history, 9 months later there have been lots more babies than in other months of the year. So uniform distribution of birthdays is actually not realistic. But let's assume it is and ask ourselves, what's the probability that if you just have a bucket and you need to put students in that bucket and you're going to put them at random locations, what's the probability of collision? And now what's the who cares question here? Well, if we have the previous scenario, a black box with 26 spots, maybe 52 spots, maybe 100, maybe 1 million spots, clearly we're going to have collisions if our hash function is as simple as checking the first letter of a person's last name. Right? The moment we have 27 students, we are guaranteed to have a collision. So that begs a more complicated or more sophisticated hash function. This is too simplistic because it's too deterministic based on inputs we know we're going to have. We're going to have 2 students whose names start with A and with B. So how can we introduce something that's going to take in a name and put it not at the 0th location, but in any old location, but a location that we can reproduce, that we can re-find by calling the hash function again? In other words, how can we spread out the inputs across a big bucket? What's a smarter hash function than just this? Yep.
Maybe you look at more than just the first letter.
OK, so look at more than just the first letter. Again, just some of these questions, even if they're starting to kind of eep over here, what's the problem? Well, just looking at the first letter is insufficient, because we're going to have multiple students with the same first letter of their last name. But you know what? We're less likely to have two students like, I regret already this name, but Adam Aardvark, because the probability of having two students whose last name starts with Aardvark, is not very likely. So just taking into account the second letter of someone's last name itself might be a good thing. Now, how do we take into account two letters? Well, this is where you have to start getting a little creative. Maybe I could take the value of the first letter and then take the value of the second letter. That gives me a number between 0 and what? And actually, we should technically do this. Let's see. Let me subtract off my capital A. And let me subtract off my capital A, so that now what I have is two numbers between 0 and 25 being added together. So we're going to get a number between 0 and 50. So you know what this means? Let me go back up here. And if our hash table is something that's storing strings, so it's storing char stars, let's call this hash table. Previously, a moment ago, my world looked like this. So that one line of code was essentially what I was describing in the form of this little milk crate. That was our hash table. But now if we can get values from 0 to 50, right? 0 to 50, well, I need more space for this at least. So does this help me here? Am I going to, yeah?
Wouldn't that set the same for someone named last name B-A and then A-B?
Perfect. So it's still perfect answer, imperfect solution here. Because now, to be clear, if we have someone's name who starts with AB, that's going to give me the same sum as BA. But that then begs the question, well, just how likely is that? You know, OK, maybe that's pretty likely. I'm not even going to try to contrive some stupid name that starts with AB. But it's pretty reasonable to expect that exists. All right, so let me just push back on you and be like, all right, let's just decrease the probability. I don't know the distribution of names in this country, but I do know that the more and more letters I tack on, the less and less likely a collision is going to be. And in fact, this is what's very often done, at least with simple hash functions. This is starting to get messy, right? This is kind of a copy-paste job. So maybe I'm at the point where I should really start rewriting this as this. Int n gets 0, and then let me do for int I gets 0, length gets strlen of s, and then I is less than length, and then I plus plus. And do you see where I'm going with this? What should I add to n on each iteration, probably? S bracket I minus A. And I can optimize this. I don't need to do all the subtraction of A all the time. But this now is already a more elegant solution, because how many letters of the person's name am I now taking into account? So all of them. So already this is more clever. So now this begs the question, if you take all of the most popular names in the world, the first names, and you start adding their numeric values of their letters together, are you going to get unique numbers? Well, no. We could, if we spent enough time, even in this room, we could probably find someone's name and someone else's name, where if you add the numbers in those names together, you get the same result for two different students with completely different names, just by chance. But the question then is, how likely is that to happen? Because it's not such a problem if it happens. Yeah, a collision would suck, but we can mitigate this by having those things called chains. We can introduce linked lists, which we'll do in just a moment. But let's see if we now can't slap a number at least on randomness. So what you proposed, adding the second letter, the third letter, or maybe adding all of them together, is a good thing, because it's just taking in more input, right? It's kind of adding, in this pseudo way, some randomness. But let's just simplify with a model we can wrap our minds around. Suppose we just use a random hash function. Suppose instead, this is such a waste of time, I'm completely conjecturing. Let me just do this. Return something like rand times 26. And I'm going to return an int, right? This returns a number from, 0 to 1. Let's multiply it by 26. This will return a random number. So that's pretty good. And in fact, if I don't do this as 26, if I actually add in some other numbers here, I can return a number that's not between 0 and 26. I can return a number between 0 and 1,000,000, 0 and 50, however big I want to make my buckets. But how likely is even a random approach to give us a collision? Well, this is one of these very sort of famous but simple problems. What's the probability that two students in this room have the same birthday? Well, we could kill a lot of minutes by actually polling everyone. Say, who has January 1st? Anyone? January 2nd? January 3rd, January 4th. It would have been really cool if we had 2 January 4ths because we'd be done. All right, let's cut it off there, though, and try to model this mathematically. All right, this looks a little complicated, but if you think about it, it's not. So what's the probability that 2 students in this room have the same birthday? Well, this is one of those statistics problems where it's actually easier to answer the opposite question. What's the probability that 2 students don't have the same birthday? And then you take that answer and do 1 minus that answer, and then voila, you have the answer you care about. Well, this top expression there, the probability of given n students, well, what's the probability that the first student in the room has the same birthday as someone else? Well, or rather, how many different birthdays can the first student in the class have that no one else has? Well, you can have any of the 365 birthdays, because you're not going to collide with anyone if you're the first student. So that's like 365 over 365, which is the number 1. But the second student who walks in the door, that student cannot have that same student's birthday. So that second student can have 364 birthdays divided by 365. So now the product of those 2 numbers is the probability that those 2 students do not have the same birthday. Okay, now the third student walks into the room. 2 birthdays have been used up. So now we have 1 minus 2 over 365 times 1 over 3 minus 365. In other words, if you just compute the probabilities that this student has this, does not have the same birthday times the next students, how many birthdays can they have, the next one, the next one, the next one, you get a very complicated formula that in the end, actually it's not all that complicated, but it looks like this, right? Which might remind you a little too much of certain math classes you never loved. But it's not all that complicated to derive. So that begs the question, what is this? Because that itself looks a little scary. Well, it's a lot easier for our purposes to graph it. And the interesting takeaway is this. If you have a room full of n CS50 students, the probability that 2 of you have the same birthday, put another way, the probability that 2 of you will hash, given a random hash function, to the same location in that black box is strikingly high, which is to say the probability of collisions in hash tables is just by nature very high. So what is this y-axis? The y-axis here says probability of a match. What's the probability that 2 students or more have the same birthday? The x-axis here is the number of students in the room. So what's kind of mind-blowing is that if you just have a class of 40 students, you have a 90% chance that 2 students, at least in that class, have the same birthday. And my God, if you've got a class of 346 students like we do, I mean, you are kind of literally off the chart, but you've got to have someone with the same birthday, probabilistically, even though 346 is less than 365. Probability-wise, you're going to have that collision. So what is the takeaway? The whole point of the birthdays is just to make concrete this idea that if we have any kind of data structure that we're putting students into, objects into, we're going to have collisions. So the motivation here is, how do we fix this problem? Well, the obvious solution is if you're running out of space at a given location, just start making more space. Start chaining students. Start chaining your outputs from that initial location, because now, do you have any upper bound on the number of students you can fit into your data structure if instead of putting the students in the array itself, you're simply adding the student to a linked list that begins at that location in the array? Do we now have this same upper limit? Doesn't feel like it, right? Because even though the height of this table is fixed, 31 being 31 birthdays here, 31 days in actually, what was the motivation here? Yeah, it was day of the month, this particular picture that we stole from the book there. So what happens when 2 people have the same birthday, or 2 people hash to the same location? You can't put them physically at the same spot, so where do you put the second person? After them, right? Or before them, whatever. Keep it sorted, keep it unsorted, doesn't really matter. Just put them in that list. But what now is our running time of insertion? What is our running time of searching? Is it constant time anymore? So it's definitely not, right? As soon as you start seeing arrows and lists, like now this data structure is devolving back into what? Something linear. But I can push back. Suppose that we have k locations. There's k buckets, 31 in this case, 26 in this case. That actually means that my running time isn't that big O of n students, but they can go in any of k locations. Doesn't that mean my running time is big O of n over k? Right? It's not linear. If it were linear, that would mean that it's big O of n, And so that means that my longest chain is going to be n students long. But wait a minute, I have all of these other chains I can put students into, k of them. So doesn't that mean in the worst case, my chain is going to be of length k, and therefore my big O running time is n over k? There's a bug in my logic here, yeah?
So it depends on what your hash rule is, because if you hash everything into the same k, that's n.
Good, good. So if your hash function is bad or just simply broken or simply stupid like this, what is the running time? Whoops, what is the running time of, in fact, finding a student? It is, in fact, always n because you're putting every student in the same location. Now, this is the extreme. Odds are you're not going to be so naive as to implement this as your hash function. But what if you're just unlucky, right? That's what big O notation is kind of about, asking questions like, what is the worst case? Well, in the worst case, you're really unlucky. Everything is backwards. Or all students' names start with the letter A. That's really bad. So even if our code does say s bracket 0 minus big A, maybe just with some probability this happens, well, this then begs the question, what is the ideal hash function? In other words, it puts the burden on you, the computer scientist, to figure out what is the best function to use here. It's probably not checking the first letter. It might not even be checking all of the letters in the alphabet. Maybe you need to do something more intelligent. And the teaser here is with problem set 6, which we'll release on Friday. This is going to be our last problem set in C. You're going to have to implement the fastest spell checker possible. And by coincidence, those inputs are going to be words. You're going to be handed an empty file that you need to fill with a function that somehow loads 140,000 inputs, 140,000 words into memory. So you're going to be implementing this black box. How do you do that? Well, every time we feed you another word, 140 plus thousand times, you're going to have to decide where to put it inside this black box. What's going to be inside the black box? Well, that's going to be up to you. You can use an array with 140,000 locations. And you can load all those words into memory pretty damn fast if you're just using an array. But what is your code going to suck at if you're just using an array? So search, now granted, if you keep them sorted, then you can do big O of log n. And that's definitely better than n and certainly n squared. But again, we're trying to get to constant time. And constant time is, again, that ideal. So the real cleverness in problem set 6 is going to be what hash function should you use so that you can actually put these words at the smartest location possible. Now, as for this question, what is the running time of a hash table? Here is finally when we see a data structure where theory no longer is necessarily consistent with reality. And by that I mean this. Asymptotically, a hash table is, yes, big O of n over k. But what do we always do every time we talk about big O and omega with constant numbers? We kind of ignore them, right? Because we said it's not interesting, because hardware advancements will take away that constant factor within 18 months, right? The algorithm itself will just get faster because hardware is faster. So we always crossed out constant values. K is constant, because when you compile your program, you're choosing K. Or when you run your program, you're choosing K, making that many buckets, and then using that many buckets. So in fact, a hash table asymptotically is big O of n. But here's this. This is where reality should break off from theory. In the real world, doing something, navigating a list that's 1/k the size of a list of size n, like that is, in real world seconds, human time, much faster. It's a factor of k faster than searching the whole list. So hash tables have this interesting property where, even though they're still a linear data structure, yeah, in the worst case, your chains might devolve into these really long beasts if you're unlucky or foolish. Well, if you're smart and your data has some properties like English words tend to, various patterns and distributions of letters, your hash table doesn't need to have really long chains. In fact, ideal would be to have chains that are roughly the same length, because code that runs in O of n over k time is, in real world terms, much faster than code that runs over in just n time. And so the challenge of pset 6 is going to be to leverage these real world implications of performance improvements to implement the fastest spell checker possible. So let's take our 5-minute break here. All right, we're back. So this slightly retro song reminds me of other comments, which some people love the music we play in 50. Some people think my music tastes are like 2 to 3 years out of date. And that's kind of true. I rarely add songs to this iPhone, but I did add this song, even paid like $1.29 for it. Those of you who are fans of The Office, anyone? Yeah, so I had never even seen the YouTube video that they recently spoofed, but now I'm kind of into this song like a year or so later. So anyhow, we'll maybe link to the video or conclude with it as you walk out today. So quick reframing then of where we came from and where we're about to go. So the motivation was to come up with a data structure that puts to shame the things we've looked at thus far, arrays and linked lists. Constant time is what we want. But unfortunately, constant time's not really possible unless we waste a ridiculous amount of memory or come up with the so-called ideal hash function that puts every student in his or her right place without collisions, but that's hard. And so we seem to be at the point now where we kind of got to compromise, right? We have to pick a size for our hash table, 31 in this case, 26 I kept saying in that case. And we're going to have collisions, but let's at least have a way of dealing with them. We can deal with them with linked lists, and now we can in fact fit an arbitrary number of words or students or objects into memory, but still find things faster in n over k time than we could with just something linear, like a linked list. So what might this look like in code? Well, let me go ahead and open up something like this, hash table.c. This too is empty by default. And just as I think aloud here, how would I implement a hash table? Well, we kind of did it a moment ago. If I'm just going to store student names or words, maybe for pset 6, we could call this my hash table. I need to pick a size. For problem set 6, you're probably not going to want to pick 26, probably not going to want to pick 31, because when you have 140,000 words, I mean, you might actually want something that's like 1,024 locations long, or maybe even longer, 100 locations long. You'll still have some collisions. 40,000 or so words won't fit, obviously, in this table. So you'll have chains. But what will be true about those chains if your hash table is this big? They're really short. So again, trade-off, right? More RAM, more memory, but faster running time. And so what you'll find in problem set 6, even though the competition aspect of it is purely for fun, opt in, don't need to do it if you don't want to, but if you do test your code following the directions and post the speed of your code and the amount of memory you're using on the course's website as part of that problem set, you'll see that some of the fun actually is in turning knobs, so to speak, tweaking constants like 100,000 and seeing if I get more buckets, does my code speed up? Or does it mean I'm using so much memory that the computer's actually finding things slightly more slowly? So this will be really the first problem set where you really appreciate real-world considerations like tweaking settings like this. All right, so what do we do now for my insert function? Well, what is problem set 6 going to have you do? Well, you're going to have a function called insert or add or something like that. Actually, the function you'll see is going to be called load, and you'll be passed a whole file, not a single word. But let me implement pseudocode for an insert function. I need to insert one word, s, into my hash table. So what am I going to need to do? I'm going to have to find a location for s. And then what do I want to do? Insert s at that location. If collision, append to chain. So that's the essence of inserting a node into this list. How do you actually find something? Well, let me just, for spell checker, I don't care about location here. Let me do a true-false thing. So I'm going to do bool, and then I'm going to do find, and I'm going to take in as input a word. And the question being asked is this word in your dictionary? I just need to say yes or no. So I'm going to do the same thing, really. Find the location for s, because hopefully it's there already. And then, then return true if found. If you've never seen the terminology IFF, is not a typo. It means if and only if. The implication is return true if it's found, else false. But if we want to be a little more pedantic, we can say else false. So this is kind of problem set 6 in a nutshell. Now, granted, it won't be just 2 lines of code. It won't be terribly many. The problem set will ultimately be more about thought and then about experimentation with actual knob turning, so to speak. But this is really what it's going to be about. But the discretion is going to come in then as to how big should this table be and how do you implement those chains. Well, there was a reason 2 weeks ago we passed out that source code for linked list manipulation. We looked, I think, at the find function and the insert function. You realize, lest you forget next week, you actually have an implementation of linked lists in your hands or in your binders, and that's probably going to be very useful for implementing support for collisions, because you've been handed essentially the code that will implement chains. But what you're going to have to figure out is, how do you have not one linked list, how do you have 31 or 100,000 linked lists and actually add and remove, add words and then find words in this dictionary? But it turns out there's other approaches to dictionaries and to hashing in general. The real new idea today and on Monday was this idea of a hash function. Rather than take some input and just put it in some fixed location, we now have some dynamism. This hash function that takes input, massages it a little bit or analyzes it a little bit, and then extracts from that analysis an answer like location 0 or location 1. This is kind of a cool thing, and hashing in general is nice, so why don't we just use it to the extreme? There are these data structures called tries. Silly name derives from the word retrieval, which for some reason is pronounced different from the word tries. But a trie is a tree. The word tree was already taken, as we'll see in a moment. So a trie kind of looks like this. This is a really nice simplification of a trie. A trie is a tree. What's a tree? Think of a family tree, right? You've got like grandma and grandpa up here, and then all of their children as these leaves and or edges coming off of them, and then it forks out. So it's a big upside down tree, a family tree. That's what a tree is in computer science context. So you know what each of the nodes in this family tree called a trie is? It's actually an array. So another approach fundamentally to implementing a dictionary, especially for lots of words, is you start with a root node, which is an array of size, let's say 26. And let's assume all lowercase, just alphabetical letters, no hyphenated words, no apostrophes in our dictionary, very simple words. So my root node is a node containing an array with 26 letters. And you know what? How do I check if a word is in this dictionary? Well, I hash on the word letter by letter by letter. So here's my first node. I've got A through Z in here. I take in a word like apple, and I look at the first letter, and it's an A. So A in a trie will typically map to 0, because it's the 0th letter. So what does that mean? That means I check the A location in my array. So location A, it's not depicted there in the top node, A. And then where do I go next in this tree? Well, I look at the second letter of my word. My word was apple, so P. So now I follow what's essentially going to be a pointer, an arrow to another node, but the arrow I follow is from the location in the array that represents P. So in other words, I have a tree, each of whose nodes is an array, and so to find whether or not a word is in this data structure, I go from node to node to node to node to node, following the arrows appropriate for the ith letter in my word, and then I get to the bottom of this tree, and as this particular textbook depicted it, at the end of your tree, the so-called leaves, you have to have a special value, a Boolean, true or false, that says a word stops here. Because if a word stops here, what does that mean? Well, it means it was inserted at one point. So now I can answer questions of the form, is this word in my data structure? Yes. Now this we'll come back to this in just a moment, but think tree, think use of arrays, and think multi-level hashing. Hash again and again and again, not just once. And we can get to this endgame. And this is what some of you will likely adopt for experimentation's sake for problem set 6. So let's frame the new jargon. What is a tree? It looks a little something like this. You have a so-called root node, and we'll use trees again in a week or two's time with web programming and HTML and PHP. A tree in computer science speak is a node, depicted here as a circle. Those nodes might contain values. Here, that node contains the number 1. And trees can have children. A left child, a right child, or in fact any number of children, although trees with just left and right children are very common. They're called binary trees, bi meaning 2. But this tree is just meant for jargon's sake. This thing up here is called the root node. 3 is a child of 1, 2 is a child of 1, 2 is a sibling of 3. So they completely stole the family tree terminology. There's nothing new here. And then finally, anything at the very bottom that itself has no children, we call a leaf. So this is a tree. And this is a specific instance in computer science of what's called a graph, where a graph is something with nodes and arrows and edges that go elsewhere. But a tree is nice because you have no circles, right? It's a very rare thing for a tree to have a branch that then grows back into itself, right? Then it becomes a graph. More on that in a data structures class. So this is a tree. This is a binary search tree. I'm just going to make mention of this because this is the kind of stuff you can revisit in the data structures course. We used binary search on arrays. Turns out you can use more sophisticated structures like trees and actually find data pretty fast. A binary search tree is a tree that's binary. Each node has no more than 2 children, left and right. And it's a search tree in that if you store numbers in each of the nodes, so long as you store them in a smart way, you can find things as fast in a tree as you can in an array that's also sorted. What does this mean? Well, notice that 55 is the root. That's kind of arbitrary. What's not arbitrary, that its child on the left is smaller than the root, and its child on the right, 77, is larger than the root. And that principle applies to all of the other children recursively. So notice 77's children. On the left is a smaller number. On the right is a bigger number. So if you adhere to this pattern in a tree, it turns out you can search this thing in log n time. And this just hints at some really cool data structures in computer science. There's things called 2-3 trees, red-black trees. The world has really leveraged this idea of a tree to come up with very sophisticated data structures. And when we, in a couple of weeks, use PHP and MySQL, a popular database engine, the database world is replete with use of trees because you can do really fancy things. And if you like this kind of stuff, CS124 is the place to go in the spring or beyond. So let's, though, use trees to solve a problem and then come full circle back to this idea of tries and then finish the day answering the question, how well can we do with storing things like words? All right, so there's this thing called Morse code. Some of you might know what it is. You kind of push that thing, beep, 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 and it sends messages and it receives messages. And it's pretty efficient because if you want to send the letter A, you just hold down a button quickly, and then you push the button for like a slightly longer time, and that's what a dash means, a dot and a dash. So Morse code is a really cool way of encoding information. And so the domain-specific topic we'll introduce, just for the sake of discussion today, is compression. So how many of you ever compressed a file before on your computer? Right, it's pretty commonplace these days. In fact, almost any web page you download these days is compressed, but then it's immediately decompressed by your browser before it shows you it. In English, what does it mean to compress a file? Make it smaller, right? So you've got a really long document, and compressing it means you make it smaller. All right, I can make your essay smaller. So if you just wrote a 10-page paper, I can compress it by deleting pages 6 through 10. Is that compression? So it actually is compression. There is compression called lossy compression, L-O-S-S-Y compression, and that's actually a valid technique. It's not so good for essays, but it's reasonable for movies and graphics, right? If you've ever looked at a YouTube video, some of them are pretty low quality, but that's because someone compressed them, and that person compressed them lossily. It's really hard to say this word. Lossily. That means they made it smaller by throwing out some of the fidelity, some of the quality, and that might be reasonable. But with English and with text, generally bad to throw away information. So there's also lossless compression, L-O-S-S-E-L-E-S-S, lossless compression. That's good for things like text. So how in the world could you take a 10-page essay, whether it's written in Notepad or Microsoft Word or Pages or whatever, how conceptually could you make something smaller without throwing away words and important theses and supporting paragraphs? What has to happen if you've got a text file with words, none of which you can afford to get rid of? Sorry? OK, so you get rid of all of the spaces. Right? You can actually, it'd be a fun exercise in XPOS or something. Really annoy your preceptor. Just eliminate all spaces. Right? That's really easy. Control-R, space, then replace all, and really annoy someone easily. Or you can do stupid things like maybe you just let's take that, which is kind of crazy, and slightly improve on it by saying just capitalize the first letter of every word, so then at least a human can more easily see where the word breaks are. But there, too, you're losing information. So a space is a legitimate grammatical construct, and we're throwing away information if we take that approach, but we're saving space. What else could we do besides actually affecting the quality of the document?
So you can provide like the most common word, and you can have like a symbol for that word, and then replace each print of that word.
OK, good. So if you use the same word a lot, why don't you just replace that word with the letter X and tell your TF, much like you would a computer science TF, X equals American history, or something that you don't want to keep saying again and again and again, right? Just declare a variable, declare a constant at the top, right? and then AH all over your document, right? That's another way to annoy your humanities teachers this week. OK, so that's actually pretty reasonable and speaks to a really clever idea. Look for patterns. Look for some places where you're spending a lot of bits and spend fewer bits, but communicate the same ideas. Factor out the common cases. Well, you might recall this chart from weeks ago. We had ASCII-table.com. The funny thing about ASCII is that you're using 8 bits to represent every character on your keyboard, plus some others, right? This whole chart is kind of overwhelming because there's so many characters. But in your English essay, your XPOS essay, I mean, how many of you are very often using the caret symbol? Or the tilde, if it's an English document and not like Spanish? Or, you know, what else is not that common? Plus, probably don't use plus that often. How many of you use the synchronous idle key on your keyboard? Probably not that much. In other words, ASCII is itself not very efficient because it spends 8 bits on every letter, irrespective of the frequency of that character in your English prose. So maybe we could take this idea of finding patterns, common words, to the real extreme and look for common patterns of bits, right? If I see the bit pattern 11111111 a whole lot, maybe I can represent these bit patterns more succinctly. And in fact, you can. When you use on Mac OS or Windows the compress file feature or the zip file feature, any of these kinds of ideas, you're taking not necessarily text documents. You can compress almost anything sometimes and make it smaller without sacrificing quality. And if we do this not at the alphabetical level, but rather at the bit level, we can do this pretty effectively. And how many of you, for instance, have taken a big file, whether it's a movie or something else, compressed it? That's made it smaller. But have you tried compressing it again? I mean, this is kind of fun. Take any file, compress it. Take your essay, compress it. It will make it smaller. Do it again. It'll make it smaller and smaller and smaller and smaller until you can compress anything you've written into what? Hopefully 1 bit, right? All right, it's kind of crazy talk, right? That should not be possible, right? And so there's actually an interesting upper bound here that's very theoretical. There's interesting ideas of entropy and randomness here, because at some point, the only way you can really compress data is to eliminate patterns, right? Or exploit patterns and replace them with shorter sequences of bits. But eventually, if you do this again and again and again, at some point, your document is essentially going to look random. You're not going to have long patterns of bits. You might have a 1, 1 and a 0, 0, but you're not going to have 20 1s in a row over here and over here and over here. You're going to essentially turn your document into something that's very random in appearance. And that's sort of the end game with compression. And encryption does the same thing. It tries to make everything look random, so there's an interesting relationship there. But the question for today is, how can we go about compressing data? Well, that is not the way. We could do something succinct like this. Why use 8 bits? Why don't we use something like Morse code, where you represent with a dot the letter E and the letter A with a dot dash, as it's called. And the reason for the different shapes here is dot means the person running the show would push a switch like this really fast, and a dash means their finger goes down for like a second and then comes up. But there's a problem. If you are the recipient of a letter in Morse code and you receive a dot dash and then some other stuff, what letter or letters have you just received? Yeah, you might have received A, dot dash, or you might have received ET. So the problem with Morse code, at least, is that it's not, there's this ambiguity. Which is it, right? So you could maybe insert pauses, and this is what they did in the Morse code world. You kind of hesitate before sending the second character, or you infer from context what the letter is. But there's the problem that we need to address. If we're going to compress information, we really can't have there being ambiguities in our zip files or in our compressed files, because you don't want to compress your essay into this and then get back a different essay, essentially, by having the words decompressed differently. So we need something called immediate decodability. Now, the formal algorithm we'll look at for a second here is actually this, if you want to read through the specifics. But I think it's easier to think through just with simple pictures. And it turns out one of the neatest applications of this data structure trees, and thus the motivation for this context, is compression. So this is how you can compress data using a fairly simple but sophisticated data structure. Suppose, for the sake of discussion, I wrote an essay that looks like this, between quotes, right? It's complete nonsense, but assume it's not. We just need a very simple alphabet here. So I've got a lot of A's and E's, but what's interesting is there are some patterns there. I see just at glancing up at the board, there's lots of EE patterns or EEE patterns. And the goal, as you proposed, is let's try to factor those out, or let's represent those more succinctly. Now, what I did here in advance is I counted up all the E's, all the A's, all the B's, and so forth. This is their relative frequency. So if you do a sanity check, 20% of the letters in this nonsense essay are A's, 10% are B's, 10% are C's, and so forth. So I did a frequency analysis. I opened the file, went from left to right, counted up the letters using an array, and now I have my percentages. This is all it takes to compress this file intelligently. I'm going to do the following. I'm going to build a forest of trees. And we're going to do this not in code today, but in words. So a forest of trees is 5 trees, each of which represents a letter. And inside that node, I'm going to put the frequency of that letter. So think of these as my leaves for the moment. But it's a forest of trees. And that, you know what, I actually have 5 trees here. It's just they don't have any children. So they're kind of stupid-looking trees. But we're going to build them up into something more interesting. Mr. Huffman, a graduate student 50+ years ago, came up with the following algorithm for compressing data. Analyze the frequency of your text, your essay or whatever, though we can do similar ideas on binary encodings too. Analyze the frequency and start building one tree out of all of these letters by taking the 2 smallest nodes and combining them into a new parent node. So this is step 1. Make your forest of trees just by copying those frequencies. Step 2 is join the 2 smallest nodes, 10%, 10%, and make a new node and put the number in its node that's the sum of the children. So we had 10%, 10%. This new node, the parent, is 20%. OK, so now repeat. And one of the concepts, we don't use all that much in this course because it's hard to do it in a compelling way until problems become more interesting, is recursion. But what I'm going to say is recurse. Apply that algorithm again. So what does that mean? Find the 2 smallest nodes. Well, I see 20% and 15%. Let's go ahead and merge those. So I merge those, new parent, 35%. But now notice what Huffman proposed. He said take the edges and arbitrarily but consistently label them with a 0 or a 1. So a 0 is going on the left, a 1 on the right, and then again and again. The goal is to make one tree all of whose edges have 0s and 1s, because that's going to be the new sequence of bits we should use instead of ASCII for Mr. Huffman's scheme. So 35% and 20%, we're going to get a new node now, becomes 55%. Finally, the 2 smallest nodes are the only 2 nodes, 55 and 45%. And thanks to percentages, everything adds up to 100%. So now I have a tree. This is a Huffman tree. This is a data structure you could fairly easily build out in C code. In fact, if we were to implement each of these nodes with some C code, with a struct, what pieces of data do you need inside of the struct? So I say struct node. What goes inside of a node to implement this data structure? One such node. So let's arbitrarily this guy. How do I embody the information 0.45 in a struct? What data type do I need inside my struct? So like a float, float f. Call it whatever you want. But what else do I need for a node to implement this picture? Yeah, you need star. So we need like a struct node star for a left pointer and a struct node star for a right pointer. There's no new concepts here, because remember, we did this with linked lists. Every node in a linked list had a next pointer. And on the quiz, the doubly linked list had a next and a previous pointer. So it's the same idea. We're just now saying not next and previous, but left and right. And conceptually, they point downward instead of laterally. So a struct might look like this. So we have frequency. And actually, I flipped it around. Float would work too, but frequency would also work if you just use the original raw numbers. Apologies for that. Either approach is fine. We might want to retain the symbol, though, right? For the leaf nodes, those actually have characters. We need to remember those. So that's a char. And then struct node left, struct node right. So how do you actually compress information? Well, what Mr. Huffman said at this point in the story is if you want to represent the letter A, do not use the binary number for 65, because that's a waste of bits. That's 8 bits. If the only letters in your essay are A through E, you absolutely don't need 8 bits per letter, right? That's just a waste. You never use those other characters. So you can probably infer, how do we represent the number A according to Mr. Huffman? 0 followed by 1. And for letter B, what bit sequence? Yeah, right. And again, it is this simple. Just I'm starting from the root, and I'm going from root to the letter B. What path am I taking? A 0, 0, 0, 0. Mr. Huffman said use 4 zeros for B. What about C? Good. And D is 0, 0, 1. And E is finally 1. And now notice what's cool about this. So it's, the data's already on the board, but let's go back to picture 1. What was the most popular character? So E, 45% of the time do we have E's in this document. So this is what's beautiful about Huffman coding, is that Mr. Huffman said, you know what? Just use a single bit, the number 1, to represent an E, because my God, if the whole idea is to use the fewest bits possible, well then optimize the common case. And this too is a theme in programming or computer science. If E is the most common letter, then my God, use the fewest bits you can to represent E. And for something like B and C, 10% of the time, fine. Waste some bits on those letters because they happen less often. And now per this comment about immediate decodability, unlike Morse code, where we very quickly saw a problem, notice what's neat here. Does the letter E share a sequence, a prefix, with any other letter? The only letter that starts with 1 is E. So that's good. We can't conflate it with any other letters. How about A? A is 0, 1. Does any other letter start with 0, 1? So no, and that's a really cool property, because with Huffman coding, not only can you compress information by using fewer bits, there's also no ambiguity. So to compress a file with Huffman coding, you, 1, analyze it, which takes big O of n time. You've got to count your characters left to right, and you build up a tree in memory using fairly familiar, even though we won't code them until problem set 6, fairly familiar constructs like structs with pointers inside of them. You build up 5 nodes, and then you loop over your nodes. And you find the 2 smallest ones, create a new parent node, link them together, repeat until you're out of nodes. And then you just traverse the tree. And there exist actually recursive algorithms that are just a few lines of code that could spit out a little table in memory or an array. That's actually kind of an interesting design problem itself. But then finally, you analyze the file for frequency, you build your tree in memory, you figure out your encodings. The last step is to iterate over your file, your essay, top to bottom, left to right, one last time. And every time you see an A, you use the function fwrite or something similar to spit out a 0 and a 1. Anytime you see an E, you spit out a 1. Anytime a D, this pattern. Then you close the file, and voila, you have a file that now mathematically has been compressed optimally. That is, you've used as few bits as possible for the common cases, and you've spent more bits, as is appropriate, for the less common cases. So for pset 6, you'll have this opportunity to implement your own tree structure, known as a trie, or your own hash table, known as a hash table. So more on that on Monday.
I begged them not to. I know you specifically put this song on your do not playlist.
Yes, I did.
I'm sorry.
Go ahead, I think it's your turn.
Wait, what happened? You're okay with this?
Yeah, I'm okay.
Okay then.
Okay. Did you see this? It was on YouTube.